Look at our solar system, and you'll find a world right next door that scientists have long called our twin sister. This image shows our own Earth, a vibrant, habitable oasis. But just a few million miles away sits our closest planetary neighbor, a world born from the exact same cosmic material. They are nearly identical. Venus shares roughly the exact same size, mass, and gravitational pull as Earth. Even their internal elements, silicon, oxygen, iron, and magnesium, are practically a match. If you could rewind the clock 4 billion years, that physical resemblance was even stronger. Back then, Venus had vast oceans of liquid water and a mild climate where microscopic life could have thrived. Two planets, built with the exact same ingredients, placed right next to each other in the solar system. Today, one is a sanctuary for life. The other is a toxic wasteland. How did two identical worlds suffer completely opposite fates? To understand what went wrong, we have to look at what Venus is today. The surface temperature sits at a blistering 464 degrees Celsius. That is hot enough to instantly melt lead, making Venus even hotter than Mercury, despite Mercury being much closer to the Sun. Then there are the physical anomalies. While Earth and almost every other planet in our solar system spin counterclockwise, Venus rotates backwards. If you were standing on its surface, the Sun would rise in the west and set in the east, and it spins incredibly slowly. A single rotation takes 243 Earth days to complete, but it takes only 224 days to orbit the Sun. That means a single day on Venus lasts longer than its entire year. Normal planetary mechanics seem to have entirely broken down here. To figure the physical mechanics of its destruction, we have to go down to the surface. Concentrations of sulfuric acid form a dense yellow cloud layer about 60 kilometers above the surface. While it actually rains acid here, the ambient heat is so intense that the drops boil into vapor before they ever hit the ground. Above those clouds, the winds whip around the planet at 100 meters per second. The atmosphere completes a full rotation every 4 days, meaning winds move 60 times faster than the planet itself spins, a mismatch called superrotation. Dropping below the clouds, the air clears, but the danger spikes. The atmospheric pressure on the surface is 90 times heavier than on Earth. Standing here would feel exactly like being crushed under a full kilometer of deep ocean water. That pressure is so extreme that the carbon dioxide atmosphere stops acting like a normal gas. It condenses into a supercritical fluid, an unusual state of matter, neither fully gas nor fully liquid, pooling and sloshing across the rocks. Survival on Venus requires enduring lethal heat alongside an entirely different state of matter that we simply don't experience on Earth. During the Cold War, the Soviet Union launched dozens of spacecraft at Venus. Most never stood a chance, melting or crushing like tin cans the second they hit that brutal atmosphere. A few heavily armored probes, the Venera landers, managed to survive just long enough.
They touched down, capturing the only direct photos of the rocky, yellow surface. They transmitted data for mere minutes before heat and pressure destroyed them. We needed a way to see the whole planet without landing on it. In 1989, NASA's Magellan spacecraft arrived. By bouncing radar waves from its massive dish straight through the thick, opaque clouds, Magellan successfully mapped almost the entire Venusian globe from orbit. The radar data revealed a surface shockingly free of ancient impact craters. Instead, 85% of the planet is paved over in smooth, hardened lava. It is dotted with massive volcanoes, some towering 8,000 meters high, and many are showing signs of active, violent eruptions even today. Venus remains a highly active geological engine. The toxins in its atmosphere weren't there from the start. They were vented into the sky by a specific sequence of planetary events. Here is how a paradise dies. 4 billion years ago, as our young sun gradually grew hotter, the oceans on Venus began to evaporate, rising up to blanket the entire planet. As the sun's radiation penetrated the atmosphere, that water vapor trapped the heat from escaping back into space. More vapor trapped more heat,
pushing temperatures exponentially higher in an unstoppable feedback loop. Venus lacks a magnetic field. As the water vapor rose higher, harsh solar winds ripped the hydrogen out of the atmosphere and swept it into space, permanently destroying the planet's water supply. Scientists call this the Runaway greenhouse effect. It is the precise, invisible mechanism that suffocated Earth's twin, leaving behind only a dense layer of carbon dioxide and a burning surface. Yet the story of Venus might not be entirely over. In 2020, researchers detected traces of a gas called phosphine high in the Venusian clouds. On Earth, phosphine is almost exclusively produced by living microbes, hinting that microscopic life might be clinging to survival high above the toxic surface. This detection has sparked new ideas for exploration, like NASA's HAVOC concept. The plan bypasses the molten rock below. Instead, humans would live in giant airships floating 50 kilometers up in the atmosphere, where the temperature sits at a comfortable 27 degrees Celsius and the pressure perfectly mimics Earth's. If humanity ever establishes a foothold on our sister planet, we won't conquer the ground. We will have to survive in her skies. We study Venus because we need to understand the mechanics of a broken atmosphere. On Earth, global temperatures are climbing. We are pumping immense amounts of greenhouse gases into the air, and we watch massive glaciers collapsing into the oceans as a direct result. The physics of heat capture are universal. Venus serves as the absolute cosmic extreme of a greenhouse process left unchecked, showing us the physical limits of planetary heating. Venus is a terrifying mirror hanging in the night sky. It proves that even a twin planet's climate is not guaranteed to remain stable, reminding us of the high stakes involved in protecting our own fragile atmosphere.